Hello, welcome to Advanced Composites. Today is the last day of the ongoing week, which is the 9th week of this course. Over this week, we have discussed this principle of virtual work for several scenarios, and we will continue this discussion today and maybe also a part of the next week. And here, what we plan to do today is bring out another facet of this principle of virtual work. So, what we have shown till so far is that the principle of virtual work says that the integral of the error force and the virtual displacement, when you integrate it over the overall domain of the problem, then if you make it 0, then this helps you get the solution for the problem. So, this is one way of looking at things. Another way of looking at things was, which is the second way, was that we said that because the virtual work is equal to 0, it implies that the error force and the virtual displacement, they are mutually orthogonal, because only then your overall work is going to be 0. If they were not orthogonal, then the virtual work will not be 0. That was the second thing. The third way of looking at things of this Galerkin method, or this whole approach which we have been discussing, is from the standpoint of least errors, and this becomes particularly significant in context of the special Galerkin method. So, we will say that this is the third interpretation of special Galerkin method. So, what does it mean? So what I'll first make the statement and then we will see what it means. It says that this method ensures that square of squared error integral is minimum. So, I first made the statement and now we will look at it, that what it means and why is it like that, and we will explain it using an example. So, again we will consider the example of a beam. The beam is simply supported. This is x, this is L over 2, this is minus L over 2. It is simply supported, so W is 0 at both ends, moment is 0 at both ends, uniformly loaded. So, all the good stuff which we had discussed earlier. So, this is Q naught. So, for this the governing equation is EI d4 W over dx 4 minus Q naught is equal to 0. Now, if W was exact, then this error in the equation, force error, will be 0. So, we assume that approximate function, consider W naught as A cosine pi x over L. Okay. So, this, why did we choose this? Because this function satisfies the value of W as equal to 0 at both ends. So, it satisfies kinematic boundary conditions. So, what is the error? Error is equal to EI A pi over L cosine pi x over L. So, this pi over L is to the power of 4 minus q naught. This is the error. This is the error in force. Now, what we do is we square this error. We take this error and square it, and then we integrate the square of this error over the domain. So, what do we do? Minus. So, this is, and let us say what it gets us. So, what we are doing is this error, I am squaring it and integrating it over the domain. Okay. So, what do so this is minus L over 2 to L over 2, and the error is EIA pi over L to the power of 4 cosine pi x over L minus q naught dx. So, this is the square of error. So, let us call it, so let us call this I, some integral I. Okay. So, what is this integral? Oh, so this is the square of the error integrated over the domain, and that I call it I. Now, I want to minimize this integral I. Suppose I want to minimize this integral, because if I want a good solution, then this integral, this square of error should be less. So, for minimum I, what should be the case? Some derivative of I should be equal to 0 for a minimum or extreme maximum. Now, once I have for minimum I, so before I do this, let us explain some things. So, once I evaluate this I, what will happen? I will depend only on A. It does not depend on I and E because they are constants. A is, see, A is unknown, it can change, but I will depend only on A. It does not depend on x. Why does it not? Because once I have done the integral, x goes away. It does not depend on E, it does not depend on I because these are constants, and it does not also depend on q naught and L. So, it depends on A only. So, if that is the case, then for minimum I, del of I over actually del of should be equal to 0. If I have to minimize I, so I can say that del of this integral, this has to be 0, and because this involves only A, I can move this derivative inside the integral. If it was involving x and other things, then I cannot do, but here it is. So, I can say so when I differentiate this with respect to A, this is what I get. So, this when I am differentiating it, I am differentiating this with respect to A. So, this is 1 plus into the derivative of this term, yeah, into the derivative of this term I, A goes away, pi over L to the power of 4 cosine pi x over L dx is equal to 0. This is what I get. Now what I do next is I take this and this constant away. So I get 2 EI pi over L to the power of 4 minus L over 2 EI A pi over L to the power of x cosine pi x over L minus q naught times cosine pi x over L dx is equal to 0. Now look at this relation. Here this term is just a constant number, the one which is in blue. So this does not influence A. Basically the aim is to find out the value of A, and how do we find out the value of A? Because we said that I should be minimum and I will be minimum if this condition holds. Okay. This is a constant, the one term in blue, so that does not affect the solution of A. The second term you look at is this term, and this term is nothing but the error, which is a function of x. Remember, this is exactly the same term which is this thing. Okay. So this is the error. And the third term, when we look at, this term, this is like your virtual displacement, except that its amplitude is 1. But in this case the virtual displacement function is the same as the displacement function of the actual value of the actual displacement function. So what that means is that if I try to minimize the square of the error the integral of the square of the error over the domain, essentially I will get the same equation as the principle of virtual work, okay, with the condition that the virtual displacement field will be similar to the actual displacement field. So this means that what this means is that the special Galerkin method minimizes integral of square error. Right. So the special Galerkin method, if we are trying to solve the problem by using a special Galerkin method, essentially another way of looking at it is that we are trying to minimize the square error integral. So that is what I wanted to talk about. So in that case, this special Galerkin method is special not only because of the choice of displacement fields, but also because it reduces the square error. So that is why it gives even better results than regular Galerkin method. So this is what I wanted to discuss today. We will continue our discussion on virtual work methods even in part of the next week, and hopefully we will close it maybe in 2 more lectures. But once again I wanted to emphasize the importance of this particular method. This is a powerful method where we have to only worry about the kinematic boundary conditions, and once we get some functions which satisfy the kinematic boundary conditions, then we can use those functions to find the solution of the problem. These solutions are approximate, so they may not give us the exact solutions, but if we choose a sufficient number of terms in the problem statement, then we can very rapidly converge to accurate solutions. So that's pretty much what I wanted to discuss over this week. I look forward to seeing you next week as well. Thank you.